Hi, this is Matt McCormick of the Department of Philosophy at California State University, Sacramento. This is one of my lectures for my Philosophy of Artificial Intelligence course. This week we're looking at Stuart Russell's new book called Human Compatible Artificial Intelligence, and specifically we're starting in on Chapter 7. Okay, so some background. We didn't get to some of the important issues that Nick Bostrom raised in his article about the control problem. With Bostrom, we considered a range of strategies for controlling a superintelligent AI. He talked about boxing, either physical or informational boxing. Talked about generating incentive methods to try to incentivize or direct the AI. He talks about stunting, tripwires, and so on. There's one component here we didn't talk about much in class that's important background for Russell's argument, and that's this discussion of what Bostrom calls motivation selection. And the question here that sort of comes to everybody's mind is, well, why can't we just program the robot to treat humans the right way directly? Why can't we just make it care about the things we care about, and as a result, we'll be safe from whatever sort of world-destroying activities it might engage in? Okay, so the way Bostrom frames this is, imagine we give it a kind of direct specification of what it's supposed to do. Endow it with directly specified motivation system. It might be consequentialist, it might be a set of rules, and famously this has already been explored at great length by Isaac Asimov in the 1940s. We haven't made a lot of progress on this question since 70 years ago. So you may have heard of these rules. Asimov says, build your robots so that first, a robot may not injure a human being or through inaction allow a human being to come to harm. A robot must obey any orders given to it by human beings, except where such orders would conflict with the first law. And a robot must protect its own existence as long as such protection does not conflict with the first or second law. And on the surface, that sounds great. Sounds like it might be a good plan. It might be a way to structure what this thing cares about. And Asimov wrote a whole series of stories, short stories that got published in the 40s, exploring the nuances and the details and the concerns that come up with the three laws. And most importantly, it looks like Asimov designed these to show that they won't work. So, it's old news that Asimov's three laws won't actually work. Even Asimov didn't think they'd work. That was part of the point of the stories. That's what creates all the dramatic tension in them. But Bostrom's going to explore some of the details here, and let's elaborate on exactly what the problem is, and then we can see what Russell's trying to deal with in building this AI his way. Okay, so Bostrom asks a bunch of questions, and the point of these questions are that they're not easily answered, or if they're answered the wrong way, it's disastrous. So in pursuing the three laws, what should the robot do? Should the robot minimize the probability that any human being comes to harm? How does the robot balance a large risk to a few humans coming to harm versus a small risk to many humans being harmed? How do we define harm? How should physical pain be weighed against architectural ugliness or social injustice? Is the sadist being harmed if he is prevented from torturing people? Who counts as a human being? What about other morally relevant creatures? What about digital minds? What about animals? There's a long, long list of questions here that aren't answered by just saying, well, don't allow any humans to come to harm or maximize, so the benefits to humans. And Bostrom starts to worry or starts to sort of spin out on the possibilities here. Imagine if we take the consequentialist perspective here and just define it as maximize the expectation of the balance of pleasure over pain in the world. How do you put that into computer code? We think we understand that in English when somebody tells you that, and you can sort of imagine in your thoughts what sort of scenarios that might play out. But how exactly do you put that into C++ or into Python or into the language that you're actually programming the machine in? How do you specify the details here? They're very important. And we're also talking about a super intelligent AI, right? So it's got vastly orders of magnitude more intelligence than any of us, and it sets about trying to achieve that goal or that purpose. So at the end of the day, suppose one of Bostrom's sort of dark fantasies, suppose filling the universe with hedonium. What's that? Well, that's matter that's been optimally organized to generate pleasure. So this machine has realized that generating the balance of pleasure over pain in the world, it can be done even perhaps without the sort of ordinary human bodies. Maybe we'll just reorganize the matter to make sure there's enough happiness out there, or maximizing happiness. Maybe it implements billions of digital minds, and it strips out all the other cognitive functions. And then as a result, these things are all having this sort of waves and waves of hedonic pleasure, but everything else that's human in human life, every other aspect of human experience has been stripped out and eliminated. And pretty clearly what Bostrom's worried about is that some tiny error here in describing or cashing out how this thing pursues that maximized pleasure goal could result, it could be disastrous. The universe gets filled with unconscious computational processes that are worthless. They're equivalent of smiley face stickers being Xeroxed trillions of times over and over again. At the end of the day, we're not actually just trying to maximize pleasure straight up. John Stuart Mill famously worried about this, different qualities of pleasures and how to balance them. And we don't have sort of, moral philosophers have been embarrassed here. We don't have clear answers to exactly how do we go about achieving this optimization. And the problem is you put a super intelligent AI to work on this project, and maybe they unknowingly end up pursuing or building out that goal in some completely disastrous fashion that wipes out humanity or wipes out everything we care about. So we have to be immensely careful about how we structure this thing's motivation, set of motivations. Okay. So that's important for understanding. That Bostrom piece is important for understanding what Russell's worried about. He's worried about how do we build in the value function, the things that the robot cares about. How do we instantiate those into the system? That's important to set Russell's argument up. And then also, I think it's important for us to spell out or do a bit of expected value theory review for those of you who've had it. For those of you who haven't, I'll try to explain it sort of from the ground up here. So part of what Russell's doing here is he's invoking expected value theory to inform his discussion in decision theory about how you build robots to make decisions. So very roughly, we could say actions in the real world never have certain outcomes, and there's a range of things that could happen with probabilities attached to each one of those, and we attach different values to those outcomes. Okay, so what does that mean? That's pretty abstract. So imagine I might park illegally for 10 minutes while I run into Starbucks for coffee. And as a result, I'm either going to get a ticket or I won't get a ticket. And if I get a ticket, well, then I'm out $50. If I don't get a ticket, then I save some time, and I didn't have to put $1.50 into the meter. So the way you cash this out in decision theory is you use this expected value calculation. And here's a way of representing it kind of quasi in English. The expected value of this action, parking illegally, equals, what I've got here is two probabilities. So suppose I estimate my probability of getting a ticket at 1%. Okay, so there's a 1% chance that I'm going to get a $50 penalty. And on the other hand, there's a 99% chance that I won't get any consequence, so it'll be zero. So the weighted average of those utilities, where utility here is being measured in terms of dollars, the weighted average of this action is I'm out 50 cents. That action, were I to do that action over and over and over again, on average, if 1% of the time I'm getting a $50 ticket, then this action per action cost me 50 cents. So that's a way to think about the probability times the utility of that action. a way to sum up what the how to treat parking illegally is to think of it as in terms of, okay, parking illegally, each case, it cost me 50 cents. Whereas the expected value of paying the meter is $1.50. So if I pay the meter, I'm out $1.50. If I park illegally in this case, I'm out 50 cents. So in this particular case, it looks like if dollars are all I care about, it looks like the better, more reasonable, more rational, the more instrumentally rational choice is to park illegally, because I save $1 by parking illegally. Now, if I've got something wrong here, if I've misestimated the utilities, if it turns out that tickets are $75 or tickets are $200, or if it turns out that the probability of getting a ticket is higher than 1%, say it's 10%. Well, if that probability of getting a ticket is 10%, then I'd be at $5 per instance of parking illegally, which is way worse than paying the meter, which is at minus $1.50. So getting the probabilities right, and this is me navigating the world, making estimations about what the probabilities of things are out there, and then acting accordingly. Getting the probabilities right is really important, and getting the utilities right is very important. And expected value theory says, well, the expected value of an action is this sort of weighted average of the probabilities times the utilities. And one way of looking at that is, here it is, also more abstractly, but put in English, the expected value of action A equals the probability of outcome 1 times the utility of outcome 1 plus the probability of outcome 2 times the utility of outcome 2 for however many possible outcomes there might be. So this great big gnarly formula on the bottom is the very abstract way of representing expected value theory. And all it says is that the expected value of action X equals all of these for every possible outcome of X, labeled X1 through XK. And for all the probabilities for X1 through XK, we do this multiplication problem, and then we add all those together for the full range of possible outcomes. So that represents a little more mathematically the same thing we've just explained in English. Okay, so what's that got to do with robots? Well, Stuart Russell's going to use this idea to talk about first probability distribution. So he's going to use this term probability distribution in the book. And what he means is, when I go into Starbucks and I make a call about the possible outcomes, I'm going to get a ticket or I'm not, and I assign probabilities to those various outcomes, I'm attaching a probability distribution on the outcomes. So in this case, it's really simple. It's just I get a ticket or I don't. So I've got a probability distribution for two events, a ticket or no ticket, and I've attached it. I've made the probabilities out to be 10% and 90%, or 1% and 99%. So a smart robot or a person will assign probabilities to the various possible outcomes of their actions. The better your model of the world is, the more accurate those probabilities will be. Okay, so you do this all the time. You do it without thinking about it. You make 1,000 decisions during the course of the day, and you do it based on a kind of estimation about, if I do this, what's going to happen. And you know that there could be some wildly unlikely outcomes from that. You know that were you to toss your pencil up in the air, there is a non-zero probability that it could land on its tip and balance. But you assign a very, very small probability to that, and you think more likely it's going to land on its side. Okay, so your nervous system provides you with a bunch of intuitions and a kind of intuitive physics about probability distributions of events, and your history, your experience, the things you've been through in your life give you intuitions or give you estimations about what's the probability X is going to happen. So right now, we're in the midst of this raging coronavirus public health crisis, and there's some people who are attaching a very, very low probability to it. They think it's a Democratic hoax, and then there's other people attaching a very high probability to it, and they're behaving accordingly. And the truth is the truth is out there in the world. The truth is the actual probability distribution of the virus in the world, and then there's people trying to estimate it. Okay, so when Russell says probability distribution, what he means is a smart robot, a smart AI system, is going to attach probabilities to outcomes, because we're not doing deductive logic here. We're doing inductive logic. We're making estimations or probabilities at best. That's the way the world operates. Okay, so in our formula, those probability distributions are these probability assignments where I've got the red arrows here. So that's how they figure. That's where our 0.1 or 0.9 was in the last example. Okay, next, Russell talks about something he calls a value function. What's a value function? What's a fancy way of saying the things you care about? Like there's a list of things you care about and you attach values to those. And with the example we used money to represent the value. So parking ticket's worth minus $50. But we can attach, more abstract value to it. You can say, well, that Taylor Swift concert's really, really important to me. It's one of the most important things I've ever done in my life. So I put a plus 500 on that. Whereas a cold beer, which I really love, is just worth, 6 hedons or 6 units or whatever kind of measurement metric we decide to put on the things we value. But so if a cold beer is worth plus 6, then stepping on a Lego in the dark is minus 150. That's really, really bad. So stepping on a sharp Lego in the dark is, what is that? 25 times worse than a beer is good. Maybe I'm exaggerating a bit here. We described a really bizarre person who attaches that much outrageous value to the Taylor Swift concert and attaches that much disvalue to stepping on a Lego in the dark. Okay, so the value function then is the other set of numbers that we're plugging into this formula. My blue arrows here, and it might be dollars, it might be just some other units that we attach. But we got to have a utility function is just the the value function is just the numbers we attach to let us, crank them through the expected value theorem. Okay, so that lets us now set up to talk about Russell's solution to the control problem. And what Russell's big insight here is that he's got these 3 principles. So I'm going to run through them quick, and then I'm going to make a couple more passes at them in more detail and explain what they mean. All right, so first off, Russell's first principle, the robot's only objective is to maximize the realization of human values. Okay, so first he wants to couple the robot's value function to humans. It's got to get its values from humans. Can't get it from some independent or autonomous purpose. It can't just be paper clips. It's got to be making humans happy or achieving the realization of human values, the things that we hold valuable, right? Because that's the point, is we're trying to prevent this case where this wildly efficient and effective superintelligent AI wipes us all out in the pursuit of some objective that's not what we wanted it to do. Second, the robot, at least initially, has to be uncertain about what those values are. And this is really crucial too. And this is part of the important insight about Russell's argument here, is that first you couple the robot's value function to humans. It has to get its values from humans, and it has to be uncertain about what they are. And you'll see in a minute, the problem is that if it's certain, if it knows what the values are, then it runs off with its project and leaves us all behind, wipes us out. We get this decoupling problem. Furthermore, we keep it in the dark about what they are, and then we set it up to try to figure out what they are. And what it does for that is it needs to observe human behavior. The best source of information about human values is human behavior. Don't listen to what they say. Don't listen to what their moral philosophers say in their articles. Don't look at the code. You have to watch and see what they do. And what they do will inform you about what it is that they value. Okay. So let's talk about each one of those in turn. Take the first one. Your job, robot, is to maximize the realization of human values. Okay, so Russell's partly drawing on something called the completeness axiom from utility theory here. And it sounds fancy, but it's actually not. It's very simple. For any 2 actions or options, call them X and Y, and you've got an agent, either that agent prefers X to Y, or the agent prefers Y to X, or the agent is indifferent between X and Y. It's just a really basic notion, is that, look, if I give you 2 options here, apple pie and cherry pie, you're going to look at those, and you've got to have one of three attitudes. And this is very much like the law of non-contradiction in logic, but it's just an axiom for decision theory. So if I present you with an apple pie and a cherry pie option, you're either going to like apple more than cherry or cherry more than apple, or you're indifferent to the two of them. There's no other alternatives. There's nothing else that could be true of an agent. If we can't assume that, then we can't really get off the ground here. We can't, and if the robot can't assume that about us, then it can't really function either. It might be that some people are sort of crazy. They seem to have both. They seem to contradict this rule, but it's, this is taken to be one of the sort of basic axiomatic principles in decision theory. So that is, confronted with two actions or options, you must either prefer X, prefer Y, or you just don't care. You're just indifferent about the two options. Humans have preferences, and the machine's sole purpose is to fulfill those, whatever those might be. That's Russell's first principle. And that is to say, it doesn't attach any intrinsic or primary value to its own well-being or existence. It might have instrumental value for its own existence. Its self-preservation might have instrumental value insofar as it's trying to seek to fulfill human preferences, but it doesn't attach direct primary value to its own existence. And that this is what we've effectively done, is we've built purely altruistic machines here. Their cares, the only thing they care about is what makes us happy. Their value function is enslaved to us. And that's what we want, right? You've got to have that. And Russell's point is that if as soon as you detach it from caring about our pursuits and it's super intelligent, then the game is lost and the thing is gone. The thing takes off and destroys the universe. Okay, so in effect what we're doing is we're saying to the robot, look, robot, your source for these values, when we fill in the expected value theorem, so remember the way I wrote this out before, the expected value of action A is the probability of outcome 1 times the utility of outcome 1 plus the probability of outcome 2 times the utility of outcome 2. Okay, so for the robot, the values that it plugs into those parts of the equation, it has to get those from humans. So its job is to act according to the expected value theorem, because it's just a sort of fundamental statement of what it is to be rational. It's to act in that fashion. And if you want to know more about why that's true, I discuss it in much more length in my Phil 60 and Phil 160 class, 61 and 161 class. So the point is, acting rationally means you have to act according to the expected value theorem. The expected value theorem, you need probability distributions and you need value functions. So the robot goes to assign values to the value functions. What are the various values of these outcomes? How much do I like a parking ticket? Or how much do I like apple pie? Or whatever. Where do I get those numbers? I have to look to humans to get them. Furthermore, and this is the next step in Russell's argument. This is the really smart part, right? This is the part that sort of sidesteps around Bostrom's crisis. Furthermore, we're not going to tell you what those values are. So you need to get those utilities from us, but we're not going to tell you straight up what they are. You have to figure it out from watching us. Okay, so that gives us our second step here. Keep the robot uncertain about those preferences. So this is Russell's second principle. And the idea is, look, as soon as the machine knows what our preferences are, then the danger is that it leaves us behind. Like it's ready to go now, so it has a job. It needs to maximize the achievement of human values, and furthermore, I know what they are, so now I'm good to go. And that's when you get this sort of these nightmare scenarios of all the humans get put into a concrete bunker, and the machine puts them all into comas and then puts them on a heroin drip for the rest of eternity. Or maybe it's trying to achieve happy minds in the universe, so it puts us all in a simulation, and it creates billions more of digital minds, and it puts them into this rapturous, joyous state that is perpetuated for centuries, because it thinks it knows what we value. So as soon as it has perfect knowledge, or as soon as it knows what it is we want, then what the human does doesn't matter anymore, and the machine knows what the goal is, and the machine pursues it. Okay, so we have to keep it uncertain about what it is that we want. It's trying to give us what we want, but we don't fully articulate or specify what it is we want. I mean, think about this. It makes sense, right? If you're in the world and you're trying to make decisions, under what circumstances do you slow down and go and proceed carefully? When do you proceed with caution? You proceed with caution when you're not sure about the outcome of your actions. You're not sure if they'll produce what you want. That's to say, certainty and caution are inversely related. The more certainty you have about the outcomes that are coming, then the more confidently you'll move forward and go ahead and act. The less certain you are about the outcomes, that's when you step carefully and gingerly, and you are much more cautious. And that's what we want. We want the robot to be cautious. And Russell's trying to design a robot that will always be watching us and making sure that what it's doing is going to give the right outcome. Okay, so this achieves a kind of humility. If it's uncertain, it will defer to humans and allow itself to be switched off if that's what the humans prefer. So the point here is, don't let it know fully what it's after. Keep it in the dark, keep it uncertain, and keep it inquisitive so that it keeps checking and it keeps modifying and keeps trying to improve its model about what human values are. Okay, that's how you keep the thing from destroying the world, we hope. One of the options. Okay, so Russell says this sets us up to solve this off switch problem. Previously, we saw this with Omohundru and Bostrom. We realized, look, if a robot has got some goal X, it will realize, if it's smart enough, that being shut off will defeat achieving goal X. Because if I'm shut off, then I can't, do anything. I can't achieve the thing I'm after. So I can't ever allow myself to be turned off. And I'm super intelligent, so I devise ways to ensure that all of these, stupid humans can't possibly shut me off. That's where we get some of these nightmare scenarios we were worried about. So Russell's robot sets it up to, allow itself to be turned off, because this thing its goal is to maximize the realization of human preferences, but I'm not sure what human preferences are. So I'm trying to make them happy, but I'm not quite sure what makes them happy. It might be that that given a couple of options, what would make them happy is to actually turn me off. So it sets up the incentive structure. Russell's approach sets up the incentive structure so that it might allow itself to be turned off. Whereas previously, when we've got this decoupled or got this independent goal system, it wouldn't allow itself to be turned off. Okay, so what does that mean? Russell says, it reasons that the human will switch it off only if the robot, is doing something wrong. That is, doing something contrary to human preferences. So the robot gets ready to do X and realizes, well, I can do X, or the human might shut me off. And if the human looks at my actions and is considering the possibility of either the robot achieves X or robot is off, and given those two choices, the human chooses turn the robot off, then that means the human prefers to have the robot off more than the human wants X to happen. So switching off is a viable option, and it's always hanging out there as a way to check its actions, and it's a way of expressing human preferences. Like, it's been coupled to, or it's been saddled with achieving human value functions, and as long as that's what it's after, having the AI shut down or limited or not doing something might be something that the human prefers more. So you keep a lid on this kind of extrapolation problem, or this sort of huge destruction, world destruction problem that Bostrom's worried about. So by the first principle, it wants to avoid doing anything that's contrary to human preferences. But by the second principle, it knows that that's possible because it doesn't know exactly what wrong is. It doesn't know exactly what human values are. So if the human does switch the machine off, then the machine avoids doing the wrong thing, and that's what it wants. In other words, the machine has a positive incentive to allow itself to be switched off. There are some cases where the machine will want that because it wants what humans want. it remains coupled to the human, who is a potential source of information that will allow it to avoid mistakes and do a better job. All right, so the off switch problem seems to be addressed by this by Russell's scheme. Okay, so how do I learn how do I learn what human preferences are? We don't listen to what they articulate. The best source of information, this is Russell's third principle, the best source of information about human preferences is not what they say, it's observing their behavior. And this is also because not only do we say one thing and do another, but we just can't fully articulate our preferences or in principles or lists or descriptions. We don't know. We don't have a full account. Like when you're making choices, you envision or imagine different scenarios, and then you kind of test them against, well, do I prefer this or do I prefer that? Which one do I like more? You're looking at menu options in a restaurant or something. And you're operating under some degree of uncertainty here, and you're imagining those different worlds where you've got, one dish versus another, and imagining, which one does it better for you. And if we were to sort of zoom out and try to extrapolate, well, what is all of the list of preferences you have? You don't know. You don't know individually what they all are, because you don't know what all the possible scenarios are. You might be surprised yourself by some of the outcomes, and certainly not with the mass of all of humanity. Okay, so if the preferences aren't manifest in their behavior, then they don't really have any preferences about the particular case in question. Observe the choices, and that will reveal their preferences. Even if they're very complicated, that's going to come out in your behavior. No doubt lots of us have lots of complicated behaviors, things that we choose that on the surface might not look consistent, and it would take a very more elaborate model to be able to figure out what it is that you really care about on the basis of the things you do. So simple ones like, do you choose pineapple pizza over sausage pizza? Do you choose coronavirus or isolation? Are you out on spring break on Daytona Beach right now, drinking out of the same pitcher of beer with your friends? Maybe you've got poor information about your preference structure, or maybe you just prefer to do that over being in isolation. Do you want to be a criminal justice major or go to law school? Do you want Trump for president or Biden for president? Maybe you don't want either of them, but we can describe, less or worse, which one of these is less bad. And that expresses a kind of preference for you. Okay, so when the robot then is building a model of human preferences, we don't even know what we want or what's better for us. And what the robot's trying to do is it's trying to fill out those values in that expected value calculation. It's trying to plug in values in that equation where the blue arrows point. It needs numbers for all of those. Humans are figuring it out. So what it does is we test, various outcomes against our preferences, real or imagined. And a smart robot will start watching us, and it'll watch you make 1,000 choices during the course of a day, or it'll watch movies and books and TV and millions of other people making choices every day. And it'll start modeling and trying to come up with a value function that'll let it plug in values into that equation. Those actual choices are very often different from what you report. If I asked you, what's your value system? And we might be dismayed about the difference between our own behavior and what we think we are. So partly what Russell's getting at is human behavior is ultimately the best source of information here. It's not perfect. And the robot's going to, do its best to sort of watch that and then model and figure out what those things are. Okay, so Russell thinks this gives him cause for the scheme, these three principles, gives him cause for optimism. First off, one of the simple things he thinks is in his favor is that there's a huge economic incentive to build robots that are responsive to human needs. So if you build them his way, obviously they're going to be very responsive and very attentive to human needs, because their whole reason for existence is built around, achieving our value system and watching us very closely to figure out what that is. So if the robot makes a mistake, he gives this example of a robot trying to feed the kids, and if it finds that the fridge is empty and it decides to cook the cat, to feed the kids. Boston Dynamics is very quickly going to go bankrupt as soon as that makes the evening news. So there's a huge economic incentive to build robots that really do a good job of modeling what we do prefer, right? Build good robots that don't cook the family cat. And the other sort of upside to his proposal, he thinks, is that there's a huge amount of raw data here that gives us information about human preferences. There's the way we act, and then there's all the books and the movies and the TV and all of the records of human behavior. There's massive amounts of information out there to let the thing start modeling up and figuring out what it is we're after. Okay, a couple of the things to worry about is that we're already in a very high stakes economic competition. That is, whoever leads with AI research, whoever builds the first really good or super intelligent AI system is just going to rule the world. There's no question about how powerful that's going to make them. And whoever gets there first is going to acquire a monopoly that then reinforces itself. So, Bostrom works this out in his book. But the thing is that if a nation state or a lab or some company gets there first, they're going to then be able to use the superintelligent AI to reinforce their position and to eliminate all the possibility of competition. So we've got this monopoly worry. And the other issue is that nation states are players here, not just private profit-seeking businesses. And nation state motives and goals are very different. Sometimes they're evil. You've got, I'm not suggesting that China's evil necessarily, but China is a nation state player that's very actively and aggressively pursuing AI research. Russia's doing the same. United States is doing the same. So they've all got very different sort of purposes and goals. So that's one of the things we've got to worry about here, about the control problem. Worries to, background worries that has Russell trying to solve the problem. Okay, so that's chapter 7. Russell gives us his 3 basic principles. Make it so that the robot's only objective is to maximize the realization of human values. Make sure the robot is initially uncertain about what those values are. Don't tell him what it is. And the best source of information about human values is watching human behavior. So that couples the value function in the robot to us. And then when the robot goes to enact the expected value theorem or act according to the expected value theorem, now it's plugging in those values. It's getting them from us, and it's not quite sure what they are. So it creates a set of controls on how the thing works. Okay, so next I'm going to do chapter 8, where Russell builds out some of the details here and explains exactly how this motivation structure works, especially the off switch problem. So we'll do that in the next lecture.